Chapter 2. In this chapter, we will be learning about the heat diffusion equations. We'll be deriving this equation. So, if you remember in chapter 1, we talked about two of the three things that heat transfer tells us about. The first was what is the rate of heat transfer. So, we looked at how to calculate the heat transfer rates in different heat transfer modes. The second was the mode of heat transfer. So we looked at conduction, convection, and radiation briefly, but we never looked at how to find the temperature distribution or temperature field in a given body. So in today's lecture, in this particular lecture, we'll be looking at the heat diffusion equation, which will help us find the temperature field or the temperature distribution in a particular body. So for this particular case, we will be assuming a steady state scenario. So what do you mean by a steady state scenario? So say temperature is a function of x, y, z, which are the spatial coordinates, and time t. But when we assume that when we assume a system or an object to be in steady state, it means that the temperature remains constant with time. So your temperature will not change with time. And what this tells us mathematically is that uh, if we consider t of x, y, z, and t, our time term will be 0, which means our temperature will just be a function of the spatial coordinates. So if you have a steady state uh, problem, your temperature will just be a function of x, y, z. Obviously, if your problem is one-dimensional or two-dimensional, for one-dimensional case, it will either be a function of x or y or z depending on which direction your heat is flowing. So for this problem, or for this derivation, we'll assume a small control volume. So let's assume the control volume to be in the shape of a cuboid or a cube. And let's say that the cube has dimensions of dx, dy, and dz, and the internal energy stored is est. So this makes the volume of the cube dV as dx times dy times dz. So in general, if we look at the total energy stored in a system, the total energy stored in a system will include the internal energy plus the potential energy plus the kinetic energy. But but potential energy and kinetic energy will be ignored for this course. You might have looked at this in your physics course. So we will ignore the effect or contribution of potential energy and kinetic energy in this course. So this brings us to the total energy stored into the system is equal to the total internal energy, which is just a function of temperature. So we can write the internal energy as little u times m, where little u is the internal energy per unit mass or the specific internal energy, and m is the mass of the body or the object that we are considering. In this case, it will be the mass of the control volume. So mass can be written as rho, which is the density of the control volume, times V. And we've seen that uh, in our scenario, the volume actually is dV, and dV can be written as dx times dy times dz. Okay, so our total the internal energy stored, or the energy stored into the system, will be uh, the integration of the specific internal energy times the density times the volume. Now the specific internal energy can be written as Cp, that's the specific heat at constant pressure, times temperature. And you might have seen this in your thermo course as well. So we will be using this definition of specific internal energy in our derivation. Okay, so moving on, let's look at our control volume and write down an energy balance equation for this. So in this case, we have a Q in coming into the system, a Q out leaving out of the system. There's a heat generation term, Q gen, and energy stored in the system is E dot St. So the energy stored in the system, like we saw in the previous slide, is CPT, which is the specific internal energy, times rho into dV, which is the mass. So this is U and this is mass. Now dV can be written as dx into dy into dz. Now taking the derivative of this particular equation with time, we get uh, del of del t times the energy stored is del of del t of the CPT into the density of the body, or the control volume in this scenario, into dx dy dz. So our energy equation, or the energy balance for the system, will be EST, or the energy stored, will be equal to Qin minus Q out plus Q gen. So Qn in this scenario, because this is a 3D space, Qn will be Qx, that's the heat coming in from the x direction, Qy and Qz, that's the heat coming in from the y and z direction. And Q out can be written as Qx plus dx, Qy plus dy, and Qz plus dz. And the Qgen can be written as a Q triple prime, which is the volumetric heat generation rate, times the volume, which is dx dy into dz. Okay, so let's use the first order Taylor series expansion to expand Q of x plus dx, which is nothing but Q out. So your Q of x plus dx can be written as Q of x plus del Q by del x, which is the partial derivative of Q with respect to x, into dx. Therefore, our net heat, or Qin minus Q out, can be written as Qx, which is Qin minus Q of x plus del Q by del x of dx, which is Q out. So this is Q out and Q in. And I've just shown you the expansion for if the heat was flowing in one dimension. So this is for a 1D heat flow. But if you have a 3D heat flow, your Q in minus Q out will be uh, this, because the Qx and Qx will cancel out. Similarly, the Qy's will cancel out and the Qz's will cancel out. So the only thing that will remain will be the partial derivatives of del Qx with respect to x into dx, and the partial derivative of Qy with respect to y into dy, partial derivative of Qz with respect to z into dz, and we've taken the negative sign from here and we've taken it outside the bracket. And this is how your equation will look like in a 3D space. And let's say this is equation 1. Now we know that Qx, that's the heat flow rate, can be written as the heat flux times the area. And obviously the area will be the area perpendicular to the direction of heat flow. And using the Fourier's law, our heat flux will be minus thermal conductivity times the partial derivative of temperature with respect to x times the area across which the heat is flowing. So in this case, the heat is flowing across the area dy into dz. So that this equation is equation number 2. Now we will substitute the value of Qx from equation 2 into equation 1. So what I mean by that is we'll take this particular value and put it in this equation right here. After substitution, our right hand side will be the negative sign which we had originally, and the first term was the partial derivative of Qx with respect to x, but on substituting Qx we have the thermal conductivity times partial derivative of the temperature with respect to x times the area across which Qx is flowing, and that area will be dy times dz times dx, which was originally there. Similarly, in y direction, uh, we uh, we will have thermal conductivity times the partial derivative of temperature with respect to y, and in this case the area across which heat is flowing will be dx times dz, and we had a dy outside. Similarly, for z direction, our equation, our third term of the equation will be this times the area, which is dy times dx multiplied by the dz, which was originally there. And in the energy equation, we had a qgen term, and qgen was nothing but the volumetric heat generation times the volume, which is dx times dy times dz. And on the left hand side we had the energy stored, which was equal to the internal energy, and the equation or the formula for that was partial derivative with respect to time of the internal energy, which was Cp times T into the mass, and the mass was density times the volume, and the volume is dx into dy into dc. So if you see, you have the volume term common throughout the equation. The dx, dy, dz term is common throughout the equation, and it will cancel out on both the sides. And there's a negative sign in all the terms here. So when we take the negative signs out, it will cancel out the negative sign outside the square brackets, and it will just become a positive term. On doing that, our heat diffusion equation can be written as rho times Cp, which is the specific heat at constant pressure, into the partial derivative of temperature with respect to time, equals to the thermal conductivity of the control volume or the body times the del square T, that's the second order derivative of temperature through spatial coordinates, plus the heat generation in the body. So this equation is extremely important, and we'll be using this for solving numericals throughout this course. So please mark this equation as important. Now we can divide the entire equation by the rho Cp term, and by doing that we can define the thermal diffusivity, which is alpha, as the thermal conductivity over the density into the specific heat of the material. So all these thermal properties can be found from the appendix which is behind your book. So please go there and check the appendix as well. So uh, if we substitute, or if we divide the heat diffusion equation by rho Cp and look it in terms of alpha, the equation that we'll get is 1 over alpha times the partial derivative of the temperature with respect to time on the left hand side, and on the right hand side we'll have del square T plus the heat generation term divided by the thermal conductivity. So we can use this equation, and on solving this equation we'll get the temperature distribution or the temperature field throughout the body of interest. Now to solve this equation we need two things, and that's, if you're working in a 3D space, say you're working in XYZ coordinates, you will need 6 boundary conditions. And the second thing that you will need is an initial condition. So one initial condition. So for solving this problem, we will need 6 boundary conditions and one initial condition, and we'll be looking at some examples of how to use the heat diffusion equation in the upcoming videos.